In this analysis, we will isolate components to view just a subsection of the wheel assembly. Hiding both the tyre and rim, we see the brake assembly and wishbones connected to the knuckle upright body. This body is a simplified blank volume which we will analyse in greater detail, and it represents the design envelope and mounting points to base the optimization study on. A more representative model includes the brake and steering arm brackets, as well as pocket cuts for the rose joint wishbone connections, and an access slot to secure the nut and bolt through the joint. This takes into consideration manufacturing and assembly constraints. The rear face also has a flush finish for simpler machining and also a small fillet for clearance. The objective is to set up a topology optimization study and create a robust, lightweight design that can resist wheel loads when the vehicle is travelling around a circuit. Choosing the topology option from the simulation study pane, we can create a new study, but we will review an existing setup. We can right-click on the part in the simulation tree and apply a material. To restrain the model, we right-click on fixtures and we will create a bearing fixture applied at the central hole with stabilised rotation to keep the upright in position. A number of vehicle systems exert loads directly on the upright, and indirect loading is also experienced from body forces. Remote loads are a great way to represent these without modelling or meshing the geometry. We will add a remote force with a coordinate position referring to the centre of the tyre contact patch and ground, and apply 3 components of force simulating dynamic loading. Additional loads, such as the brake torque in the caliper, steering arm cornering force, and suspension wishbone mounting points are also included to apply a number of different forces on the upright component. Goals and constraints help define what we are trying to optimize the design for. In this case, reducing the mass by 50% while maintaining a factor of safety of at least 1.25 to achieve the best stiffness to weight is the desired end goal. Manufacturing controls help preserve areas of the geometry from being optimized or removed, meaning crucial hardpoints such as mounting locations, machined holes and reference faces remain in the final optimized shape. A 5mm ring around the 4 bolt holes will be kept for structural integrity. Other holes are preserved too, and a thickness control for the minimum allowable thickness is set to 15mm. One final preserved region needs to be added to the bearing mounting faces with a 5mm exclusion zone that can be previewed directly on the geometry, shown in yellow. Now that we have our design envelope, applied loads, required goals and manufacturing constraints, we can mesh the part using high quality, curvature-based elements with appropriate sizing. Before running the analysis, we can review the study properties to modify preserved regions and run additional baseline studies to compare with before optimizing. We'll choose the automatic solver for this analysis and accept the changes. It's time to run the analysis, which will take a while as it iterates through the various designs. We'll switch to the completed results to review the final optimized shape. The material mass plot highlights areas of the model we must keep and areas that have been or can be removed. We can see the rounding of corners around the bracket holes and removal of material on the left. This tessellated mesh body can be exported as a smooth body in a configuration in the file or exported to a separate new part. We'll choose the new configuration option and give this a name, and then choose to output a solid body file that we can work with. There are also options for grouping mesh faces together. We are then presented with a final smooth configuration which we can 3D print or design around to create a parametric body. We will first extract mass properties by isolating the optimized body and evaluating its mass. This body is around 370 grams compared to the original body volume, which can be overlaid on top and weighs over 640 grams. A body color can be applied to clearly highlight the differences in optimized topology. A general X shape is formed around the bearing mount, and a tapered loft profile can also be seen when viewed from the side, with some clear areas that can be machined out completely. These insights can be used to redesign the component into a more easily manufactured traditional shape or manipulated further for 3D printing using advanced SolidWorks tools.